Hello, this is a tutorial on how to set up a recirculation flow. In this video, I'll be showing you how to set up a sort of recirculation relationship without having to set up the recirculation pipes and all that, even without including a pump or some sort of fan in your setup. The reason for this is that we're working with oils instead of air. Now, if we're working with air, you can obviously use SOLIDWORKS predefined models for the fans and things like that. But in this case, we're working with oils. So this will be a quick tutorial on how to set up some sort of recirculation flow without having to set up all this infrastructure. Now to get started, I personally just like to use a transparency because it'll be easier once you start clicking on lids and things like that. Also, one thing to mention is that I've already set up my lids in this video. Before the video. But once we go to Flow Simulation, there is like a Tools tab that you can create these lids and place them. So without being further said, let's go ahead and start with our wizard. We're going to go ahead and name this, let's say 1 or 0.1 meter cube per second study. So let's see, we want to study how fast the oil cools down, in this case the lid, and we'll go into more detail as to what that means. Oh, it won't let me do that. Okay, so we'll just put 0.1 study. SI units, I usually do my temperature in Celsius, time in minutes. So hit next. Well, actually, we can have it in seconds, but it doesn't matter. Conduction, because we are doing some sort of heat transfer study. Time dependence, we want our total analysis time to be 5 minutes, but we could just do 3 minutes. Gravity is relevant in our study, so let's make sure it's in the right direction. It's currently not, so let's go ahead and change this. Don't forget to put the negative. There you go. And then our analysis type is internal, which is why we have the lids, so let's go ahead and put that here. And this is very important in case something is not defined. We don't want it to flip out. So our main liquid in this study will be an oil. Now this is a user-defined oil. I kind of use the help of AI to kind of create this table, but I'm sure you can find other tables, or maybe just use the pre-existing fluids here to kind of use. So we'll add it here. Make sure that it allows for laminar and turbulent flows in the study. And then let's go to solids in the model. Stainless steel is the bulk of most of the material here in this model. Now I don't really touch this because this will just be like whatever the model starts off with. Conditions will kind of determine what the pressure is in the cell and the testing cell, and the temperature. All of this will change based off whatever we put for our parameters. So we'll go ahead and hit finish here. It'll set up perfect. The lids, everything's good. So then we'll start with our solid materials. Let's go ahead and import them from our model. You can see rubber, it doesn't allow to go through because it doesn't have a specific heat, which is fine. So we'll just go ahead and substitute it for some other material. Now you could just define a material yourself and get that fixed, but I don't want to. So let's go ahead and just use a different material. In this case, for our rubber seal, we can use some sort of insulating material, which it kind of is. Nylon 66 could work, polycarbonate, polystyrene, all that could work. In this case, silicone, because most gaskets are made out of that material. And make sure you select what exactly you're applying the material properties to. In this case, the rubber seal. And then let's go ahead and set up our boundary conditions. So let's go ahead and close this out. So our inlet is here. So let's do our inlet volume flow. That's going to be what I base it off. 0.1. And then for our thermodynamic parameters, this is exactly what we're interested in. We're interested in having this change over time. So we want our input to be whatever's coming out of our outlet flow here. So for now, we'll leave it as static. So this means that it won't change over time. So we're going to use this dependency function to change it later. So we'll go ahead and set that up. boundary condition. We'll set up our outlet volume flow. And let's just set it to be the same thing as the other one. Whatever's coming in is whatever's coming out, right? Okay. Let's go ahead and add our initial condition. So this study wouldn't make sense if we didn't have something to actually study. So in this case, we're just studying how fast does this thing cool off. So we're going to put 70 Celsius. You can make 100, whatever. And then the important part in all this is setting up a surface goal or some sort of goal that is determining whatever's coming in here. In this case, surface is whatever this surface or this surface area of the outlet is. You can put average, you can put max. I'll just put average in this case, and I'll hit check. So now we have a goal. This will be important because once we go to our project and parameters, we can add a parameter. We can call this outlet temperature. And we can set this value to be dependent and not a constant based off a goal. And so this goal we're going to set up a relationship. Let's say it's 20 to 20. So 20 to 20 and 100 to 100. Now the units, it'll ask for it later, but you can kind of click here to see what the relationship is here. So if, for example, your real life model isn't exactly a linear relationship, you can always adjust this. So, and then like I said, you can change your unit. In this case, it's temperature Celsius. Hit check. All right, now we can go ahead and back to our inlet volume flow. We can go ahead and go to our thermodynamic parameters. And now we can actually use one of our parameters that we just created, outlet temperature. Let's create that 20 to 20 relationship and 100. So it's gonna, whatever values are in between, so that's linear, it's just gonna be one for one kind of. So then we'll hit OK. Now that it's dependent, we can go ahead and hit check mark. So now that it's set up, one last thing is let's make sure our calculation control options are set. Physical time is correct. Finish conditions is 3 minutes, so it's not going to wait until it converges. Goals criteria, I'll let it define itself. Solving, time steps, you can let that do on its own or manual. It's really up to you. You can just do time steps in every like second or so. Doesn't matter. And then for this one, you can save up backup files. I wouldn't, but you could. It's up to you. Physical time, start from 0, go to every second or so. Okay, so then you hit OK. Once you've set this up, you've successfully set up your experiment. And now let's wait for the results.